Hey, good evening, everyone. Welcome to O-level physics lesson on electromagnetism. Last week we went through the theory, and today we'll go through some past year exam question. Okay, let us begin. Okay, so everybody start doing question number 37. It may not be very clear, but the wire has a cross on every one of them. So all the wire has a cross. It's also written in the question. The wires have current flow going into the paper. Okay, so type out your answer. Type down the question number and your answer. Okay, Yuting, well done. Well done. Okay, since it's the first question, I'll give you some clue. Use your right hand rule. Okay, Ryan, well done. Hao Ray, well done. Bei Kwan, right hand rule. Since the current is going into the paper, your thumb is going into the paper. Okay, Bei Kwan, well done. Last two students, Qiao Xing and Oscar. What's your answer? Qiao Xing and Oscar, what's your answer? Okay, Qiao Xing, Oscar, do you need help? Okay, Oscar, I will need you to go back to the video and then watch it again. Okay, so the current is going to the paper. That's why it's a cross. Okay, if it's going out of the paper, it's a dot. Okay, so you need your thumb to point into the screen. Okay, then the direction of your finger, okay, sorry, your right thumb must point into your screen, and then your fingers will be the magnetic field line. Okay, Oscar, you try. So which one is definitely out? Xiao Xing, are you there? Xiao Xing. So you see your thumb, right? The thumb, your right thumb. Okay, not my right thumb, it's your right thumb. Your right thumb, the thumb is the direction of your current. So your thumb go into the page. Then your finger, okay, your finger, can you see? If my thumb is pointing to me, can you see the finger will be the direction of the magnetic field line. Okay, if my thumb is pointing towards you, my fingers will be into the, my fingers will be the direction of the magnetic field line. So Oscar, you try again. Qiao Xing, are you there? Yeah, I cannot hear Qiao Xing. Qiao Xing haven't entered the. Okay, everybody remove your reaction. Okay, Oscar, you're correct. Okay, so for this question, the answer is B. Okay, because if you have a cross like this, okay, if the Y is going inside, normally your magnetic field line will be in a clockwise direction. If it is a dot where your thumb is coming out, okay, your magnetic field line will be in a anti-clockwise direction. Okay, so if you look at all the four examples, If it's a clockwise direction, the right side is correct, the left side is wrong. The left side is correct, the right side is wrong. Okay, both of these are wrong. So only B is correct. Okay, so only B is correct, and therefore your answer is B. Qiao Xing, are you there? Qiao Xing, you cannot hear me, right? Okay, so let's go to the next question. Okay, if you understand this question, give me a thumbs up. Thumbs up. How are Oscar, Qiao Xing, are you okay? Oscar, you okay? Can no hard. Okay, very good. Okay, let's go to the next question. Okay, do question number 37. You all may begin. Yiting, well done. You're doing very fast, very well. Okay, Ryan, very good. Ray, very good. Okay, the key about this question is you want to make it move a smaller distance. Okay, so in exam, bring your highlighter, highlight the keywords. Bei Kwan, well done. Oscar, are you okay? So do you want to have a smaller distance? It means your force should go down. So which of these four factors will reduce your force? Okay, Oscar, can you see when the switch is closed, the wire move up. Okay, the wire move up. If you reverse the terminal, the wire will move in the opposite direction. Is that clear? Okay, so it will not have a smaller distance. If you actually reverse the terminal, the wire will move down. Is that clear? Okay, so A is wrong. Okay, same thing. If you reverse the pole of the magnet, it will also reverse the direction of the wire. Okay, so in this case, Oscar, use a lucky guess to reduce the force. Is the answer B or D? Okay, well done, Oscar. Chelsea still not responding to me. Okay, Chelsea, are you okay? Okay, let's do the next question. Okay, so very good. All of you can get it now. The answer is D. All right, very good. Let's continue. Okay, same paper, question 38. You all may begin. Okay, do question number 38. Okay, Yiting, well done, Yiting, very good. Do you all remember how the magnetic field line looks like in the first question? Oh, Ray, well done. Ryan, well done. Oscar, well done. Okay, Bei Huan, incorrect. Okay, last week I did not mention this. Okay, but I think of a very good metaphor, or not metaphor, a very good way to actually explain some certain thing. Okay, let me just go back to the first question. Okay, so all of you know that if it's two crosses, okay, for this question, the answer is B. Okay, all we understand that the answer is B is correct. Okay, so I want all of you to imagine, just imagine the magnetic field line. The magnetic field line is like a rubber band. Okay, it's like a rubber band. So if let's say, for example, in this scenario, okay, in this scenario, the A is, this is a cross. A is a cross, and then the left side is a dot. Okay, the left side is a dot. Okay, so can you see that? Imagine you got a lot of rubber band in between. Naturally, they will actually move away. Can you see? If there's a lot of rubber band in between, can you see? The two wire will move away. Now, in the scenario B, where you can see there is actually like a rubber band joining them together. Okay, in this case, they are both crosses. So the rubber band joining them together, so naturally they will move together. Is that clear? So if you were to imagine the magnetic field line are like a rubber band. So from here you can see that in the D example is actually moving together. D example are both dots. Okay, both dots, not cross. Okay, likewise for example C, there's a lot of rubber band in between. Okay, the two wire will move away. Okay, so if you just imagine that the magnetic field lines are like rubber band. If there's a lot of rubber band together, it's stronger. If the rubber band are further away, it's weaker. Okay, and then can you see down here? The rubber band will wrap around the two wire. You push the two wire together. Okay, so if I use this analogy, does it help you understand better? Okay, so Bei Kuan, for this question, you understand now? Okay, so in this case, you are to draw the field line. Okay, you know that crosses, if you use the right hand grip rule, it is a crosswise. Okay, it will be a cross. So you got two crosses. Okay, so you have two clockwise. How does it looks like? Okay, so for a start, maybe you want to draw the normal line first. So you will know that okay, so for a start, you just draw a circle first, then you look at the between. In between, they cancel each other. So in between, there should be less line. So eventually, okay, if you were to see, on top is the same direction, you can draw something like this. Okay? So that's how I draw my magnetic field line. And then from this pattern, okay, you will know that they'll come closer together because it's like the rubber band trying to bring the two wires together. And therefore the answer is C. Okay, is that clear? I still did not see the Chelsea, where are you? Okay, this question, can you write down the answer, the question number 35? Write down number 35 into the question. Okay, start doing this question. Write down your answer 35 and then your answer. So this is like a circuit breaker. We went through this before, so let's try this question. Wow, Yuting, you're very fast. I haven't even read the question. Well done, Yuting. Oh, Ray, well done. Ryan, very good. Bei Kwan, well done. Oscar, well done. And Chelsea, are you there? Chelsea? Okay, so all of you got it correct. Okay, so if you want to switch off, in this case, switch off the high current. We're talking about this one, okay? So you want to make this break. You want this thing to move towards the iron core. So which of these four answer allows the iron strip to be attracted to the iron core? Okay, the only answer will be D. Okay, so very good. All of you got this correct. Well done. Okay, well done. Let's do the next question. Do number 36. Okay, same thing. Write down the question number and then your answer. Okay, question 36. You all may begin. So this question, they did not tell you the direction of the current. So what do you think is the answer? You take again, very good, well done. First to get the answer, very good. Oh, Ray, well done. Oscar, well done. Ryan, very good, excellent. Okay, left with Bei Kwan. Bei Kwan, what's your answer? Bei Kwan, if you are not sure, just type help in the chat. Okay, let me explain to you all. For this question, what is the method you all use? What's the method you all use? You use the Fleming left-hand rule, correct? So I want all of you to point out your finger, okay, and then show me the Fleming left-hand rule in your camera. Okay, show every one of you, show me in your camera your Fleming left-hand rule. So far, I see nobody in the camera. I see a lot of aurora. I see a lot of wind. I see one gray color one. Okay, can you show me your Fleming left-hand rule, all of you? All of you, can you all of you show me this? Hello, hello. I don't want to see the aurora and the trees and the gray. Okay, so you can see my camera. I show you all my 3 fingers. Okay, my thumb, my 3 fingers. And then do you all realize one thing? Okay, you're in your school, you all have learned the X and the Y axis, correct? And you know the X and Y axis, they are 90 degrees to each other. Okay, then if I were to have an axis that's coming out of the page, okay, coming out of the page. Okay, this axis is also 90 degrees to the Y as well as 90 degrees to the X. Okay, so can you see our finger here, the Fleming left-hand rule? Can you see here? Okay, they are all 90 degrees to each other. Okay, so in the question like this, look at this question here that I put my arrow. Okay, so just imagine we have the three factors. Last week I teach you all, right, FMC. Okay, if you all remember me, you all remember FMC. So this is the M. Okay, the cable is the C. So you have to find the force. Okay, so which is the force? So these 3 must be in 90 degrees to each other. That's what you all learn in secondary school. But in real life, not everything is in 90 degrees. Okay. But what you all need to understand is that at 90 degrees to each other, the effect is the biggest. Okay, if it's 0 degree to each other, there'll be zero effect. Understand so far? Okay, so in secondary school, you all learn the maximum effect, which is 90 degree to each other. When you go to a JC or university, you all need to calculate all kinds of angle. Okay, but for now, you just need to know that they're all 90 degrees to each other. If the magnetic field line is in this angle, the current is moving in or out of the page. Your force will have to be 90 degrees to the magnetic field as well as the cable. Okay, so having said that, we know that C will be wrong because C is the same direction as the magnetic field. Okay, so C will be wrong. Okay, and then regardless which direction your current is, A, B, and D, which one actually is 90 degrees to the magnetic field? Okay, only A is 90 degrees. Okay, and then your current is either moving in or out of the page. Okay, so therefore your answer will be A. Okay, A will be the answer. Okay, by explaining like this, do you understand it better? Okay, for the maximum force to occur, your magnetic field and your current has to be 90 degrees each other. And then your resultant force will be 90 degrees to the other to your magnetic field as well as your current as well. Therefore, we use the Fleming left-hand rule. Okay, can you see when you do it like this? The three angles are 90 degrees to each other. The three of my fingers are 90 degrees to each other. So all of you look at your left hand. Okay, do you all see this thing? Okay, so for this to work, use Fleming left-hand rule. Okay, because our right hand is mirror image of the left hand, so you cannot use both. You only use the left hand for this to work. Is that clear? Okay, who thinks that what I explained now using the X, Y, Z as an example is make you understand better? Give me a clap. Okay, we think that this explanation help you understand better. Give me a clap. If there's no reaction, there's no effect, then give me a no reaction. Hey Ryan, why are you cheering? Hey Qiao Xing, are you there? Qiao Xing, hello. Okay, let's do the next question. Okay, so far you're clear. Okay, this topic is one of the hardest topic, but I hope I can make it easier for you to understand. Okay, look at question number 37. You all may begin. Okay, do question number 37. Wei Huan, you understand the previous question now? Why the answer is A? Ethan, well done. Ryan, well done. Wei Huan, well done. Oh, Ray, well done. Oscar, well done. Okay, there is only two scenarios for this type of question. Okay, I will show you the two scenarios. Okay, then you will know that this question is not that hard. Okay, one way is I let this be the north and this be the south. The magnetic field lines will look like this. All right. Clear? Okay, then the other scenario, if on the right is the north, on the left is the south, okay, it will look like this. Okay, sorry. Okay, so these are the two possible answers. Okay, the two possible magnetic field line depends on the direction of your current. Okay, so you realize that in the middle, they are all going in the same direction, either from left to right. Okay, either from left to, in this case, the first example is from right to left, and the bottom example is from left to right. Okay, so the direction of the magnetic field lines are the same, okay, in the middle of the solenoid. Okay, so for these four answers, which one has the same direction throughout? Okay, only C has the same direction throughout, and therefore only C is the correct answer. Okay, well done to every one of you. Okay, let's continue. Okay, do question number 38. Okay, you may begin. Do question 38. Okay, 北关 confused, 一婷 correct, Hori correct. Ryan, okay, 北关 correct. Okay, Ryan incorrect. Okay, so if I were to draw the two wire, the first one is coming out, the second one is going in. Okay, so basically what you need to do is just draw the magnetic field line first. The first one looks like this, am I right? The second one that's going in will look like this. Can? So where is your, so in this case, you can see this is your first magnet. So the first compass, you put the first compass here. The second compass pointing upwards. Can you see? The second compass is pointing upwards. Is here. The third compass is pointing down. Can you see that? So now, if I were to reverse these two directions of the current to become like this and like this, I reverse both the current. So what will be your answer now? Okay, Beikwan, are you clear now? Oscar, well done. Ryan, what do you think is your answer? Okay, Bei Guan, are you clear about this now? Okay, if I were to reverse, okay, let me draw the magnetic field line. Okay, Ryan, take a look. If I were to reverse, this one will be like this. And then this one going in, then coming out will be like this. All right. So if I were to put my magnet itself, my magnet will be pointing upwards here. In between, will be pointing down. Okay, here will be pointing up. So now I want you to compare this to this. Did it change? Did the compass direction change? How many change direction? Okay, Ryan, how many of the compass change direction? Okay, so Ryan, what's your answer? Okay, well done. So are you clear about this? So in this case, the answer is 3, because when you reverse the direction of the current, your magnetic field also changes, which I draw down here. Can you see this? So if you have no time to do this question, you know 0 and 1 are both wrong. Okay, 0 and 1 are both wrong. It's either 2 or 3. Why? Because the outer both will definitely change direction. You'll be confused whether the center will change. So if you are confused, just draw out. You'll be very clear that the center one also change direction. Is that clear? Can? Right, okay. Chelsea, can you hear me now? Let's do the next question. The next question. Question number 36. Okay, all of you can do this now. Okay, Yuting, Oscar, well done. Ray, well done. Ryan, well done. Okay, let me see. Okay, ignoring the direction of the magnetic field. We just observe the 4 magnetic pattern. Okay, ignore all the current. Can you see? I remember I told you all that assuming these are rubber bands. Okay, so for A and C, the pattern of A and C, can you see that it actually wrapped around the 2 wire? It wrapped around the 2 wire. Will it cause the 2 wire to come together or move apart? Okay, it will cause the 2 wire to come together because it actually wrapped around the 2 wire. So to move apart will be wrong. Okay, Bei Huan. So C will definitely be wrong because based on the pattern and the forces, it will not make sense. Okay, likewise, look at the B and D. There are a lot of rubber band in between. Can you see? There are a lot of obstacles in between. So the wire will move together or move apart. Okay, you actually move apart. So moving together, in this case, B is also wrong. Okay, so for Beikwan, you try again. Is your answer A or D? Okay, so basically, if you don't know what to do, you draw your two field line first. Your thumb, right thumb, not left thumb, your right thumb pointing into the page. How would the field line look like? Okay, in what direction? It will be clockwise, right? Okay, so Beikwan, are you clear about this now? Okay, so in this example, in between you see it is cancelling out each other. Okay, so there'll be less line in between. So your final answer will be like this. Is that clear? Okay, so the answer will be A. Understand now? Beikwan. Okay, let's do the next question. Okay, do question number 36. Okay, do this one. You all may begin. Do question 36. Eating well done. Okay, how many of you can hear music in the background? Is it too loud? Oscar, well done. However, well done. Ryan, well done. Okay, Beikwan, I want you to draw the magnetic field line on the screen. Okay, let me just draw these two things here. Can you draw the two magnetic field line? Okay, Beikwan, draw the magnetic field line on the left side. Draw the field line here first, then you draw the right side. Can you do that on the screen now? Beikwan. Yeah, I'll draw the field line. You draw the direction. Okay, you go and draw the direction. Is it clockwise or anti-clockwise? Okay, Beikwan, you do that for me. Just draw the direction. Is it clockwise or anti-clockwise? Okay, Beikwan left side is correct. How about the right side? Okay, well done. Okay, next thing is you compare the between. You compare the between, this one. Are they in the same direction or opposite direction? Okay, same direction means will they cancel each other? So how do you continue drawing? So you can actually continue to draw like this. Okay, you will have more. Okay, you have more. Okay, in the same direction. Is that clear? Then you have even more. Understand? Clear? So on top, you draw like this. Okay, on top is in a different direction. So you will not combine together. Same thing for below is in a different direction. So you not combine together. So now based on these two patterns, these two will move in what direction? Will they come together or will they move away? Okay, because there's so many obstacles in between, you actually move away. Everyone, are you clear about this now? So can you tell me what's your answer now? Okay, very good. Okay, well done. So the answer will be C. Is that clear for everybody? So let's continue. The next question. Chelsea still missing. Okay, let's do the next question. Question 36. Okay, do this question now, everyone. Okay, welcome Chelsea. Finally, I see your answer correct. Yuting correct. How about the other boys? What's your answer? Okay, so this is a DC current. DC current means current move from plus to minus. Okay, DC current means current move from plus to minus. Okay, so how would the direction be when look from the top? Okay, Oscar, well done. Ryan, your new answer is correct. Ray, your answer is correct. Okay, so from the top, we were to do the right hand rule. Okay, your magnetic field will be in a clockwise direction. Are you clear? Okay, so answer is either C or D. So now, what happens when you reduce the current? When you reduce the current, the magnetic field will also reduce. So when you reduce, what happens to the spacing? Does it come together or is there further apart? Okay, so when you reduce the magnetic field strength will be reduced. Your magnetic field lines has to be further apart. Okay, so that it shows that the magnetic field is actually weaker. So can you look at the example here? The example here, can you see? This part inside here is closer, so stronger. Then on the outside is actually further away. So therefore it means weaker. So can you just imagine when they are close together, it's like there are more rubber band, so there's actually stronger. When it's further apart, there are less rubber band, so therefore it's weaker. Okay, so for Pei Kwan, you understand the answer already? Pei Kwan, are you there? So what's the answer, Pei Kwan? Okay, so the answer for this will be D. Okay, is that clear for everybody? So we are doing the simple part of the electromagnetism. Okay, after National Day, so next week we'll have no class. After National Day, we will do the motto. Okay, so now we are doing the basics one first. Hopefully by next week, you all will be okay. Okay, let's do the next question. Do question number 37. Okay, this one. A little bit of the motor already. So this one is using the Fleming left hand rule. Okay, Fleming left hand rule. The code word is FMC. If you all remember me, you'll be FMC. So what is the answer for question number 37? Okay, Bei Kwan, try again. Oscar, well done. Yuting, well done. Okay, so let me explain to you. So this is your plus, this is your minus. So your current is moving this direction. Okay? Then your magnetic field line is moving from north to south. Okay, it's moving from north to south. So use your left hand. Okay, left hand. Fleming left hand rule. Okay, all of you try. Your M is moving from right to left. Then your C is moving from front to back. So your thumb, your left thumb is moving, is pointing up or down. All of you try again. Okay, so if you use your Fleming left hand rule, okay, this is your middle finger. This is your, okay, your left middle finger. This is your left index finger. Okay, so your left index finger pointing from, okay, your left index finger will be pointing to the left. Correct? Your middle finger your middle finger will be pointing to X. Your your index finger will be pointing to the A. Clear? So in this case, where will your thumb be? Okay, my thumb will be pointing upwards. Can you see that? Okay, so my thumb will be pointing upwards. So this will be my force. So my answer will be B. Okay, when I draw like this, is it clearer to you? Is it clearer to you when I draw like this? Okay, so so let's revise again. Revise again. So this is your index finger is your magnetism, your middle finger is your current, and then your force is your thumb. So your thumb is pointing upwards. So this is your force. Okay, if you are clear about this, give me a yes reaction. If you're clear about this, give me a yes reaction. Are you okay? Okay, we are done with the MCQ now. We'll just do 2 structure question and then we'll take a break and continue after National Day. Let's do 2 questions, or maybe do 3. Later I show you. 2018. Okay, all of you now do question 8A and then write down your answer in the chat. How many of you not sure one? Just type help. Yi-Ting, your 1 is incorrect. Your 2 is correct. Actually, your 2 is also not very correct. Try again. Chelsea, your first answer is wrong because you mentioned already there's magnetic field here. Your 2 is incorrect as well. Oscar, your 1 is incorrect. Your 2 is correct. Okay, Ryan, well done. What is your second condition? Ryan, you are actually correct. Well done. Yi-Ting, the whole question did not mention anything about current. Okay, let me guide you. Okay, so basically you have a north and a south. So basically what happened is there's a magnetic field line going from left to right. Okay, so a magnetic field line Okay, what does the magnetic field line tells you? If you have a north pole, okay, you have a north pole by itself, which doesn't occur in the world. In the whole world, north pole doesn't occur by itself. South pole also doesn't occur by itself. But if there's such a thing, you will move from left to right. Correct now? Because north and north will repel, north and south attract. So this north pole will move from left to right. But in the world, there's no such thing as a north pole. So what does this magnetic field line actually suggest? Okay, it actually suggests that if I were to put, okay, if I were to put a compass there, you will point in that direction. At the top of the compass is the North Pole. So this is your North Pole, this is your South Pole. So can you see? North and South attract, North and South attract. Okay, so you actually point in the right. So that is what the magnetic field lines tells you. So the question is asking, what are the two conditions for a particle to move? Okay, for a particle, let me read the question again. To experience a force. Okay, so we're talking about a particle experience a force. So what are the two conditions? So can you all talk about this? So in this whole example, there is no wire, there is no current. Okay, there's no wire, no current. So what are the two conditions that allow any particle can be anything, okay, to actually experience a force? Okay, so we mentioned about the Fleming left-hand rule. Okay, the Fleming left-hand rule, which is the FMC. So when there is a M, there is a C, then there will be F. Okay, so what is C? What particle is C? Because we already have the M. So to experience a force, what particle can the C be? Okay, well done, Yuting. So what is that? What can you put inside here? What particle can you put inside here so that this particle will experience a force? Okay, very good. Yuting, very good. How about the rest of you? How many of you need help? So therefore, what particle can you put inside this field so that this particle can experience a force? So who would like to try? Okay, so what is this particle? So this is a current, correct? Current. Current consists of what? Okay, moving electrons. Okay, so the two conditions are this. Okay, moving electrons. So what are the two conditions? Okay, the particle must be moving. That's number one. Okay, number two, the particle must be charged. Okay, so in this case, electron is negative charge. Okay, so regardless whether is it a positive or negative charge, this particle will experience a force. Is that clear? Okay, so this itself has to be charged. Okay, so the particle has to be charged. It can be either positive or negative charge. So it must be charged so that when placed in the magnetic field, this particle will experience a force. So for example, if this particle is moving up, down, this example is a positive particle that's moving down. Okay, so this is my middle finger. So my positive force moving down is my middle finger. My magnetic field, the red color line is my index finger. So all of you take your left hand. Okay, your M is moving from left to right. Your middle finger, because it's positive, it's conventional charge, is moving up, down. So what happens is this particle will experience a force coming out of your screen or coming out of the page. Are you clear about this? So this particle is moving up, down, experiencing a magnetic field from left to right. And this particle, as it's moving up and down, you experience a force that's moving out of the page. Okay, are you clear about this? If you are clear, give me a clap reaction. If you are clear, give me a clap, because this is something I think is quite interesting, which I don't think many of you think of this before. So are you clear about this? Have you ever think of this before? So the particle is moving down to up to down, magnetic field from left to right. The particle will be moving out of the page. That is the force that is actually being created. Do you understand about this now? So the particle is already moving up to down, but when experiencing a magnetic field in the opposite, in the cross direction, it will experience a force, and in this case, it will be coming out of the page. So the magnetic, the positive charge will actually be moving downwards and out of the page. Is that clear? Can you imagine that? Okay, all of you, Ryan, remove your reaction for now. So are you clear about this? Okay, understand about this question perfectly? So basically, the answer is just moving electron. So the first one is the particle must be moving and the particle must be charged. That's all. And you have a moving charge, you experience a force. Clear? Okay, very good. Very, very good. Let's do the next part. Today we might end slightly earlier. Depends on how we finish. Okay, now all of you do this. So now this is a very yeah, this is you just draw two lines, you get 3 marks. So who want to try this question? Just draw two lines, two arrow lines, and then you get 3 marks. Okay, just assume okay, gamma ray is an EM spectrum. Am I right? That includes light. Light is part of the EM spectrum. I'm not saying that light is part of gamma ray. So light and gamma ray are part of the electromagnetic spectrum. So let's assume we don't talk about gamma ray because a lot of us don't know what's gamma ray. Cannot imagine. Let's imagine it's light. If a light goes through a magnetic field, what happens? Will the light actually do anything? Will it move faster, move slower? Will it actually bend? Okay, what will happen to the light? So all of you think about it. You think your no for what? I don't understand your no. Qiao Xing, I will give you 1 mark. Your gamma ray part is correct. The rest of you, how would can you describe how would the two line be drawn? You think your no, I don't understand your no is for what thing? Can you explain your no? You're asking me a question? How Ray, well done. Okay, you think well done for gamma. How about the fast moving electron? How do you draw? Xiaoxing, why you change your answer? Okay, Xiaoxing, your second answer is correct. How Ray, your electron is wrong. Yeah, Xiaoxing, you got you understand the common mistake. Okay, so let me go through the first one first. Gamma ray is not a current, it's not charged, it's also not a magnetic material. So in a magnetic field, you'll do nothing. Okay, so for the gamma ray, you will just go straight, okay, with no reaction. Okay, so these are all electrons. If the electron is moving from left to right, what is the direction of the conventional current? What will be the direction of conventional current? It will be from right to left. Is that clear? If the electron is moving from left to right, the direction of the conventional current will be right to left. Okay, so this is your left middle finger. Okay, so your strong magnetic field is into the page. So your left index finger is into the page. So now, what is the force? Okay, all of you take out your left side, your fingers, your left hand. Okay, your Fleming left hand. Your left middle finger. Okay, your left middle finger is moving from right to left. Then your left magnetic field is into the page. So all of you do that now. Your thumb will be pointing up or down. So all of you tell me your thumb will be pointing up or down. If it's pointing up, the electron will be moving upwards. If it's pointing down, the electron will be moving downwards. So all of you tell me, if your left middle finger is moving from right to left because it's the direction of the conventional current, and your magnetic field is your left index finger pointing into the page. So your thumb will be pointing up or down. All of you tell me, your thumb will be up or down. It will be thumbs up or thumbs down. You team well done. How about the rest of you? How Ray, can you show me your finger? Your left middle finger, okay, your left index finger is going into the computer. Your left middle finger is moving from right to left. So your thumb will be moving in what direction? Hey, sorry, Yiting, can you try again? How Ray, well done. You're right, sorry. How Ray, you're right. Yiting, you try again. The key mistake is the direction of conventional current is right to left. Okay, right to left. Okay, that is the key mistake that most of you will make. Okay, you think well done. So what happens like this? This is your left index finger. This is your hand. Okay, pointing into the page. Then your middle finger. Okay, your middle finger will be to the left. Okay, to the left, which is your middle finger is to the left. So your thumb will be pointing where? Okay, so your force will be pointing downwards. Can all of you see that? This is your magnetic field is pointing into the page. Your middle finger will be pointing to the left. Okay, I know it's very hard to see. I also don't really understand what I'm doing. Let me redraw again a bit based on what I see here. Okay, can you see that now? Is it better now? My left hand. Okay, so my thumb is pointing down, my index finger pointing to the page, my middle finger is pointing to the left. Can all of you do the same thing in your hand, your left hand? Can all of you do the same thing? Okay, if you can do the same thing, you know that force is pointing downwards. Okay, if your force is pointing downwards, this electron will be moving downwards. Is that clear? So you draw the two blue lines, you get 3 marks. Okay, why is this pointing to the left even though it is pointing to the right? It's because the conventional current is in the opposite direction as the direction of the electron. So you're always pointing using the conventional current. Is that clear? Okay, once you are clear, Can you all give me a thumbs up? Okay, my this finger is like horrible. If you all can see, give me a thumbs up. Bei Kwan and Oscar hasn't been participating for the last two questions. I'm concerned about Oscar and Bei Kwan today because a lot of questions you all did not do correct. But Bei Kwan and Oscar, are you all clear about this? Ryan, are you okay? Today very good, Ryan. Never go toilet. Bei Kwan and Ryan, you understand about this question? Then we do the last question and that's it for today. Yeah, I hope that I help you understand this. So next week when we go into moto, it'll be even harder. Okay, this week is the basics of electromagnetism. Okay, next week you'll go into moto. Okay, let's continue. Last question for today. Okay, let's look at this question. Okay, last question, just 3 marks. Okay, just 3 marks. I will want a few of you to draw this. Let me see, who should I call? Okay, I will call a few of you. Okay, Bei Kwan, can you draw here? Okay, Oscar, can you draw on top here? Who want to try? I got 2 more space. Who want to try and raise your hand? Okay, Bei Kwan, you draw on the center here. Oscar, you draw on the top left. Okay, Hao Rui, you draw here. Ryan, you draw here. Okay, so all 4 of you start drawing. Tell you what, everybody draw. If I call your name correct, you may go. I draw 2 more. Okay, Yiting, you draw here. Chelsea, you draw here. Okay, when I see that you are doing correctly, I call your name, you may leave. Right, what is PID? What is PLD? Personal learning device. Personal learning device cannot draw. Then Ryan, you'll be the last to go. Okay, I want all of you to also draw in the circle, right? Whether is it a dot or a cross, or either, or mixture, or same or different. Can all of you do that? Draw the dot or the cross as well. All of you. That will be 1 mark. Chelsea, magnetic field line cannot cross each other. The other draw, you minus 1 mark already. Bei Kwan, in exam, we don't just draw 2 lines, or you draw a little bit more. And exam, don't need to draw so many arrows, Bei Kwan. Hey Ryan, you draw a piece of paper and then you show me on camera. Hey Kwan, can you draw more lines? Draw more lines. Xiaoxing, can you also draw a bit more lines? And Bacon, no need so many arrow lah. Oscar, enough already arrow. Don't need too many. Hey, you all know how to draw one, or you all just look at each other and then just refer. Who just joined the class? Ryan, why you got so many numbers? Okay. Well done to everybody. So very good. The first thing I want to see from everyone will be there must be a cross. Okay. The second thing that I want, wow, so now this Ryan drawing already. So Ryan want to go. Hey, suddenly you can draw. Just now you cannot draw. Mr. 122. Okay, very good. I think all of you understand this. So the last thing I want to share with you is, even though this is a card, so the wire will be experiencing what kind of force against the card? Will we be pushing towards each other or pushing away from each other? You type it out in the chat. Once I call your name, you may go. Okay, thank you, Oscar. Thank you, Howard. Well done. Thank you, Xiaoxing. Xiaoxing, the earlier part, if you miss out, can you go and rewatch the video? Ryan, well done. PT, my question is, based on this diagram, would the two wires happen to move towards each other or away from each other? Yiting, why? You look at the pattern. Why is it will it move away? Okay, well done, Yiting. You may go. Anybody else has any question for me? Ryan, Beiguan, are you okay? Okay, thank you, thank you. See you all in 2 weeks. Goodbye and good night.